And this is equal to L dIL over dt. So it means that the rate of change of inductor current over one period on the average, it's going to be a constant positive value, which means that if you know that if something is changing with a constant ratio, it means that it's always increasing, right? So it means that IL, it's going to increase. And so it cannot be in the steady state. The same way, if this was negative, it means that IL, it's going to decrease all the time. So then it cannot be in the steady state. So if we are in a steady state, the average voltage has to be equal to 0. And based on this, because IL is equal to integral of L VL dt, if this is 0, it means that the current of the inductor at the beginning of the period, it's always equal to the current of the inductor at the end of the period. Right, so this is what volt-second balance tells us. Another way of looking at this is that if we remember the definition of flux of an inductor, this is basically the definition of the flux of an inductor, or you can just like look at it as also this way, both of them. So if this is 0, it means the average flux across the inductor, it's going to be 0. It means that the input flux is always going to be equal to the output flux, and it would balance each other, and it would be equal to 0. Or in the other case, the change in the flux over one period, because delta IL is going to be 0, this is also going to be 0. Right? So like it means that the average flux of an inductor in the steady state mode, it's going to be equal to 0. Again, we can look at it in another way. Let's say like this is positive, this is negative, this is T, this is dt, this is VL. If you guys remember the definition of power, power is V times I, right? And energy is integral of power over time, right? So if I just expand this, it would be V I dt, right? And again, I'm just going to expand this even further. This is VLIL. So this VL, what's the relationship between voltage of an inductor and the current that goes through inductor? So I can replace this with L dIL by dt times IL times dt. These would cancel, so we would just basically have integral of L IL dIL, right? And so this is basically going to be over one period, it's going to be 1 over 2 LIL squared, right? Because this is just like the power 1, so it's going to be IL squared divided by 2. Over one period, the energy that gets stored in an inductor, if we are in the steady state mode, it's going to be like this. So it's going to be 1 over 2 LIL at t equal t, which is the period, squared, minus 1 over t LIL at t equal to 0 squared. And if you're in the steady state, we saw that these two are equal. So the average energy that gets stored in an inductor, it's also going to be 0. So the physical meaning of this is that in this case, excuse me, the energy that gets stored in the inductor gets released here. So if we are in the steady state mode, the average energy inside an inductor has to be constant. It shouldn't change, right? If we basically supply some energy to it, if we store some energy to it, it has to be released in the same period. So the same thing that we said about flux, it's also true about the energy. The energy has to be equal to, the average energy has to be equal to 0. So that was regarding the volt-second balance. We can do exactly the same analysis for a capacitor. There's a good duality between inductor and capacitor. So for the capacitor, we have I that goes through a capacitor, IC, it's equal to C dVc over dt. That's the dynamics of a capacitor, right? And again, if we assume we are in the steady state mode, means that the average current should be equal to 0. Means that the if this is IC average is equal to 0, it means that dVc over dt has to be equal to 0. And this means that the voltage of the capacitor at t equal to 0 has, at the beginning of the period, I'm just talking about the first cycle, the first period, has to be equal to Vc at t equal to t. And the average of the current, if we have, let's say, like a shape like this for the current of the capacitor, let's say something like that, just like this, for example. It's not realistic, but if you're in the steady state mode, the average of the current ICT over one period, so from here to here, has to be equal to 0. So the average of IC, I can write this as IC average is equal to 1 over t integral over one period IC dt. Right? So it means that this area has to be equal to this area. So the net area of the current over one period has to be equal to 0. And if, again, like you remember from your physics course, the integral of I over time, it's the charge that gets accumulated on the plates of a capacitor. So it means that the net charge over one period for capacitor in the steady state mode has to be equal to 0. So if we accumulate some charge across the capacitor plates,